Imagine driving past that lot the morning after the concrete was poured and finding a finished mansion with furniture inside. That is what the James Webb Space Telescope found when it looked at the earliest moments of the universe. Galaxies that should have taken billions of years to assemble were already there, fully formed, chemically mature, in the first few 100 million years after the Big Bang. Objects so massive and so complex that no model of cosmic history can produce them in the time available. And this is not one measurement. It is hundreds of objects, across dozens of surveys, confirmed by independent teams, all saying the same thing. The timeline we built for the universe does not work. The factories were running before the building permits were issued. What you are about to see is 3 years of evidence from the most powerful telescope ever built, data from X-ray observatories and ground-based instruments spanning 11 billion years, and a mounting case that the standard model of cosmology is either missing something fundamental or wrong entirely. It started with a single photograph, taken from 1 million miles away, of a patch of sky no bigger than a grain of sand. On July 12, 2022, NASA released the first full-color images from the James Webb Space Telescope. The target was a patch of sky no bigger than a grain of sand held at arm's length, centered on galaxy cluster SMACS 0723. The image contained thousands of galaxies stretching back over 13 billion years. Within hours, astronomers around the world began downloading the raw data, and within days, some of them started finding objects that made no sense. JWST had been in development for 25 years. It cost roughly $10 billion. Its primary mirror spans 6.5 meters across, made of 18 hexagonal segments coated in a layer of gold thinner than a human hair. The entire assembly sits behind a sunshield the size of a tennis court, folded for launch and slowly unfurled over 2 weeks as the telescope drifted to its permanent home at Lagrange Point 2, a gravitational sweet spot about 930,000 miles from Earth, where it orbits in lockstep with our planet, always keeping its back to our star. The telescope launched on Christmas Day, 2021, aboard an Ariane 5 rocket from French Guiana. It arrived at L2 on January 24th. 6 months of calibration followed. Engineers aligned the 18 mirror segments to within a fraction of a wavelength of infrared light. The instruments came online, one by one. NIRC, for near-infrared imaging. Near-spec, equipped with a micro-shutter array, capable of observing over 100 objects simultaneously. MIRI, for mid-infrared, each tuned to see light stretched by cosmic expansion from visible wavelengths into the infrared. The mission had a specific purpose. JWST was built to observe the first galaxies that formed after the Big Bang. Cosmologists had spent decades building models of what those galaxies should look like. Small, dim, simple clumps of hydrogen and helium gas, maybe 100 million times the mass of our star at most. These predictions came from Lambda CDM, the standard model of cosmology that has dominated the field for a quarter century. Lambda CDM describes a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It predicts that galaxies assembled slowly, growing through hierarchical merging over billions of years, starting as tiny seeds and gradually combining into the massive structures we see today. The first deep field image was supposed to confirm this picture. Instead, the data contained bright, compact sources at distances corresponding to the first few 100 million years after the Big Bang. They were too bright. Preliminary photometric estimates suggested masses far exceeding anything the models allowed. Astronomers flagged them, ran the numbers again, and got the same results. At this stage, nobody panicked. New telescopes always produce surprises in their first data. Calibration uncertainties were large. The photometric redshifts could be wrong. The mass estimates relied on assumptions about stellar populations that might not hold at extreme distances. Every experienced observer knew the drill. Wait for spectroscopic confirmation before drawing conclusions. The anomalies were noted, flagged for follow-up, and filed as preliminary, but the follow-up data did not make the problem go away. Over the next several months, as more surveys came online and more fields were observed, the anomalies multiplied. They appeared in JWST, the deepest survey, in CEERS, in Cosmos Webb, the widest. Different teams using different instruments looking at different patches of sky kept finding the same thing. Objects in the early universe that were too massive, too bright, and too structured to exist under any version of the standard model. In February 2023, a team led by Evo Lab at Swinburne University in Australia published the paper that turned those scattered anomalies into a crisis. The Cosmic Evolution Early Release Science Survey, known as CEERS, had identified 6 galaxy candidates at high redshift. Each one appeared to exceed 10 billion solar masses. That is 10 billion times the mass of our star, packed into a galaxy that formed when the universe was barely 500 million years old. To understand why this was a problem, consider what 10 billion solar masses means. The Milky Way, our own galaxy, contains roughly 200 billion stars and has been assembling for over 13 billion years. These 6 candidates had apparently accumulated a significant fraction of that mass in less than 1/20th of the time. The analogy that circulated through astronomy departments was immediate and blunt. Finding these galaxies was like discovering a skyscraper in a neighborhood where the concrete foundation was poured yesterday. Lab's team used NIRC photometry to estimate the redshifts and stellar masses. The galaxies appeared at redshifts between roughly 7 and 11, corresponding to the first 300 to 700 million years after the Big Bang. At these epochs, the standard model predicted galaxies of maybe 100 million solar masses. The CEERS candidates were 10 to 100 times more massive than the upper limit of any prediction. Mike Boylan-Colchin, a theoretical astrophysicist at the University of Texas at Austin, took the CEERS results and pushed them further. His 2023 paper in Nature Astronomy, which framed itself as stress testing the lambda CDM model, calculated something remarkable. If you took the mass estimates at face value, these 6 galaxies collectively contained more stellar mass than the total baryonic budget of the universe should have allowed at that epoch. The universe simply had not produced enough matter to fill them. It was as if someone had spent more money than existed. The paper landed hard. Headlines called them impossible galaxies. Cable news ran segments. Social media exploded with claims that the Big Bang had been disproven, which it had not. The actual situation was more specific and more interesting than the headlines suggested. The Big Bang itself was not in question. What was in question was everything that came after it. Lab CEERS paper acknowledged the uncertainties. Photometric redshifts are estimates, not measurements. They rely on the brightness of an object across multiple filters to infer its distance. Without spectroscopy, which breaks light into its component wavelengths and identifies specific emission or absorption lines, the redshifts could be wrong. A galaxy that appears to be at redshift 10 might actually be at redshift 3, with its colors mimicking a more distant object due to dust or unusual stellar populations. The astronomy community responded the way it should have, with skepticism. The masses could not be right, critics argued. The instruments were new. The calibration was still being refined. Photometric redshifts at these distances had never been tested against spectroscopic confirmation because no telescope had ever been capable of providing that confirmation. JWST was, for the first time, operating in territory where there was no independent check. So, the community waited for spectroscopy, and when spectroscopy arrived, it told a story that was more complicated than either side expected. The spectroscopic follow-up began in late 2023 and continued through 2024. Teams using NIRSpec targeted the CEERS candidates individually, breaking their light into spectra and searching for emission lines that would pin down their exact redshifts. The results came back mixed, and the story that emerged was messier than the original headlines. First, the critics were partially right. NIRCam's calibration in its first year of operation had systematic offsets. The photometric pipeline overestimated fluxes at certain wavelengths, which inflated the inferred stellar masses. When the data was reprocessed with updated calibration, some of the mass estimates dropped, in certain cases, substantially. Second, some of the redshift estimates shifted. A few candidates turned out to be at lower redshifts than initially estimated, meaning they were closer and had more time to form. Others were confirmed at their original high redshifts, but with revised masses. The 6 galaxies that had launched 1,000 headlines were no longer all sitting at 10 billion solar masses. The media moved on. The corrections made for a less exciting story. Galaxies, slightly less massive than previously thought, does not generate clicks. The crisis, as far as most coverage was concerned, had been resolved. Science had self-corrected. Everything was fine. Everything was not fine. The revised masses were still too high. After every correction, after recalibration, after spectroscopic confirmation, the galaxies at high redshift remained significantly more massive than lambda CDM could produce. The corrections had shaved the numbers down from impossible to merely inexplicable. Boyle-Kolchin's fundamental calculations still held. The early universe contained more stellar mass than the standard model's baryonic budget permitted at those epochs. In 2025, a team running the Renaissance simulations offered another avenue of reduction. They demonstrated that if the first generation of stars followed a top-heavy initial mass function, meaning a disproportionate number of massive stars formed compared to modern populations, the inferred masses from JWST photometry would drop by roughly a factor of 10. Massive stars are brighter per unit of mass, so fewer of them are needed to produce the same luminosity. This was a legitimate physical argument. If the earliest stellar populations were dominated by heavyweights, then what looked like 10 billion solar masses of ordinary stars might actually be 1 billion solar masses of very bright ones. A factor of 10 reduction sounds like it solves the problem. It does not. Even at 1 billion solar masses, these galaxies at redshifts above 10 exceed what hierarchical assembly models predict by a wide margin. The top-heavy initial mass function reduces the tension. It does not eliminate it. This pattern, where a correction reduces a crisis from dramatic to merely persistent, is worth paying attention to. It happens often in science. A dramatic claim generates attention. A correction follows. The public loses interest, but the underlying anomaly survives the correction. It sits quietly in the data, waiting for someone to explain it. The overcounting scandal, as some astronomers began calling it, did not prove the crisis was fake. It proved the crisis was real, but less photogenic than the first round of papers suggested. So the question shifted. If the galaxies are real, and their masses are genuinely higher than predicted, even after every reasonable correction, then something about how stars formed in the early universe was fundamentally different from anything the models assumed. The question was no longer whether JWST found something strange. The question was how the early universe managed to turn gas into stars with an efficiency that no known physics can explain. Star formation efficiency is one of those numbers that sits quietly at the foundation of astrophysics. It holds up a lot of weight without attracting much attention. It measures the percentage of available gas in a galaxy that actually converts into stars over a given period. In the modern universe, that number hovers around 10%. Roughly 90% of the gas in a typical galaxy never becomes a star at all. The reason for this low efficiency is well understood. Stars form inside dense clouds of molecular gas that collapse under their own gravity. But as soon as the first stars ignite, they fight back. Radiation pressure from hot young stars pushes surrounding gas outward. Stellar winds carve cavities in the cloud. When the most massive stars die as supernovae, the explosions blast remaining gas out of the region entirely. This feedback cycle limits how much gas any single episode of star formation can consume. Turbulence within the gas cloud adds another break, preventing large-scale coherent collapse. 10%. That has been the number everywhere astronomers have looked, across galaxies of different sizes, at different distances. in different environments. It appeared to be something close to a universal constant of galaxy physics. And then JWST found the blue monsters. Blue monsters are a class of galaxies identified in the Sears and JADE surveys at redshifts above 10, corresponding to the first 400 million years after the Big Bang. They are tiny. Their radii measure between 100 and 400 parsecs, which translates to roughly 300 to 1300 light-years. For comparison, the Milky Way spans about 100,000 light-years. These galaxies are smaller than some individual nebulae in our own galaxy, but their ultraviolet output is extraordinary by any measure. Their UV spectral slopes, designated by the Greek letter beta, come in at -2.5 or steeper. This indicates stellar populations that are young and hot, almost entirely unobscured by dust. They are blue because they are furiously producing massive, short-lived stars that burn through their fuel in a few million years. The stellar masses inferred for blue monsters range from 100 million to 1 billion solar masses. Given their compact sizes and the available gas supply at their epochs, the star formation efficiency required to produce these objects exceeds 50%. Some early estimates from Sears data push toward 100%, every atom of available gas becoming a star. No known physics achieves this. The feedback mechanisms that limit efficiency to 10% in the modern universe should have been operating in the early universe as well. If anything, the denser conditions of the early cosmos should have made feedback more effective. The gas was hotter. The radiation fields were more intense, and yet these galaxies converted gas to stars at 5 to 10 times the expected rate. Something suppressed the feedback, or something accelerated the collapse. Nobody has identified what that process was. The blue monsters raised the stakes of the JWST anomalies from a question of mass to a question of mechanism. It was no longer enough to say the early galaxies were surprisingly large. Now the question was, how? How did physics work differently in the first few 100 million years? And the blue monsters were not the only evidence that something fundamental had changed. JWST also found chemical signatures in the early universe that should have taken billions of years to appear, starting with an element that has no business existing at the dawn of time. In January 2024, a team led by Stefano Carniani confirmed the redshift of a galaxy designated JWST 14-0 using roughly 10 hours of near-spec spectroscopy. The redshift came in at 14.32. That made it the most distant spectroscopically confirmed galaxy ever observed, seen as it existed just 290 million years after the Big Bang. 290 million years. To put that in perspective, if you compress the entire history of the universe into a single calendar year, with the Big Bang at midnight on January 1st, JWST 14-0 would appear on January 8th. The galaxy existed in what cosmologists call the cosmic dawn, the epoch when the first sources of light were just beginning to switch on in a universe that had been dark since recombination. The galaxy spans roughly 1,600 light-years across. Small by modern standards but remarkably well-defined for its epoch, its luminosity and inferred stellar mass both exceed what lambda CDM predicts for objects at this redshift. But the mass and luminosity were not the biggest surprise. The biggest surprise was what Carniani's team found in the spectrum: oxygen. At 290 million years after the Big Bang, the universe was supposed to contain almost nothing except hydrogen and helium, the two elements forged in Big Bang nucleosynthesis during the first few minutes of existence. Heavier elements, which astronomers call metals regardless of whether they are actually metallic, are produced inside stars through nuclear fusion. When those stars die, they scatter those elements into the surrounding gas through stellar winds and supernova explosions. The next generation of stars forms from this enriched gas, lives and dies, and enriches the gas further. Each generation adds to the chemical complexity of the universe. Oxygen is the third most abundant element in the cosmos today, after hydrogen and helium. It is produced primarily in the cores of massive stars, those above roughly 8 times the mass of our star, through the carbon-nitrogen-oxygen fusion cycle. These massive stars live fast and die young, typically within 5 to 10 million years. But producing detectable oxygen in a galaxy requires multiple generations of massive stars, living, dying, and seeding the interstellar medium with progressively more enriched material. The standard timeline for this process allows for hundreds of millions of years at minimum. Finding oxygen at 290 million years after the Big Bang compresses that timeline almost to its breaking point. Some models can accommodate it, barely, by invoking extremely massive first-generation stars that formed immediately and died within a few million years, enriching the gas for a rapid second and third generation. But these models require precisely the kind of high star formation efficiency that the blue monsters already demonstrated was problematic, and they require it even earlier, at higher redshifts. JWST 14.0 held the distance record for nearly 2 years. During that time, it became one of the most studied objects in extragalactic astronomy. Teams analyzed its morphology, its spectral energy distribution, its chemical abundances. Each analysis added detail to a picture that remained stubbornly difficult to explain within the standard framework. Then, in January 2026, the record fell, and the galaxy that broke it was even harder to explain because it contradicted the models and the other record holder simultaneously. The galaxy designated MOMZ 14 was confirmed in January 2026 at a redshift of 14.44. That pushed it past JWST 14.0 by a slim margin, making it the most distant galaxy ever observed. The light from MOMZ 14 left its source roughly 280 million years after the Big Bang, just 10 million years earlier than the previous record holder. 10 million years is cosmologically insignificant. At these redshifts, the difference between 14.32 and 14.44 corresponds to a sliver of time barely distinguishable in the models. What made MOMZ 14 remarkable was its size, or rather, its lack of size. JWST 14.0 measures roughly 1,600 light-years across. MOMZ 14 measures approximately 240 light-years across, nearly 7 times smaller. Two galaxies existing at essentially the same moment in cosmic history, separated by an insignificant gap in time, and yet one is almost an order of magnitude larger than the other. This was not supposed to happen. The prevailing models of early galaxy formation predicted that the first galaxies would share broadly similar properties. They would form from similar initial conditions, under similar physical processes, and produce similar results. The cosmic dawn was assumed to be relatively uniform, a period when the first structures emerged from nearly identical seeds scattered by quantum fluctuations in the early universe. Finding two galaxies at redshift 14 with wildly different sizes destroys that assumption. The diversity of the earliest galaxies implies that multiple formation pathways were already operating when the universe was barely 280 million years old. Whatever process built JWST 14.0 into a 1,600 light-year structure did not operate the same way for MOMZ 14. And whatever compressed MOMZ 14 into a 240 light-year package did not affect its neighbor at nearly the same epoch. This matters because it means the earliest moments of galaxy formation were more complex than any model anticipated. A single explanation for the anomalies, whether top-heavy stellar populations, unusual gas accretion, or anything else, would need to account for objects being dramatically different from each other, spanning a huge range of sizes at the same epoch. The problem is not that the early universe made galaxies too fast. The problem is that it made several kinds of galaxies too fast, through mechanisms that appear to have produced a range of outcomes that the models cannot reproduce. MOMZ 14 is still being studied. Its compactness raises specific questions about its stellar density, its formation mechanism, and whether it contains the same chemical signatures as JWST 14.0. Spectroscopic analysis is ongoing, and the results will either deepen the diversity problem or reveal some common thread connecting the two record holders. Consider the scale. 240 light-years is roughly the distance from our star to Arcturus and back, 60 times over. That is the entire width of a galaxy that formed when the observable universe was smaller than the distance between the Milky Way and the Andromeda Galaxy today. But JWST was not done pushing boundaries. Before the telescope reached deeper into cosmic dawn, it had already found something closer in time, but far more disturbing in its implications. A black hole that sat at the center of a galaxy 470 million years after the Big Bang. And this black hole weighed as much as every star in its galaxy combined. The galaxy is called UHZ1. It sits at a redshift of approximately 10.1, which places it 470 million years after the Big Bang. JWST did not observe it directly. UHZ1 lies behind galaxy cluster Abell 2744, one of the most massive galaxy clusters known. The cluster's gravity bends spacetime around it and acts as a natural magnifying glass. This is gravitational lensing, first predicted by Einstein, and now routinely used to observe objects too faint or too distant for any telescope to see on its own. Abell 2744 amplified the light from UHZ1 by a factor of roughly 4. JWST's infrared cameras identified the lensed galaxy, but identifying it was only the first step. The critical observation came from Chandra, NASA's X-ray Space Observatory, which has been operational since 1999. Chandra stared at the same patch of sky for more than 2 weeks straight, accumulating photon by photon, a faint X-ray signal from an object whose light had traveled 13.2 billion years to reach the detector. 2 weeks of exposure time for a handful of X-ray photons, each one carrying information about conditions in a galaxy that existed when the universe was 3% of its current age. The X-ray emission told the team, led by Priyamvada Natarajan at Yale University, that UHZ1 harbored an active galactic nucleus. A supermassive black hole was feeding on surrounding material, heating it to temperatures that produce X-rays. This alone was notable at such an early epoch. But the mass estimate is what made the result extraordinary. The black hole at the center of UHZ1 weighs approximately 40 million times the mass of our star. That is large for any black hole. But the real number is the ratio. In the local universe, supermassive black holes typically account for about 0.1% of their host galaxy's total stellar mass. The black hole at the center of the Milky Way, Sagittarius A star, weighs 4 million solar masses inside a galaxy of several hundred billion. It is a tiny fraction of the total. UHZ1's black hole weighs as much as every star in its galaxy combined. The ratio is not 0.1%. It is somewhere between 10 and 100%. That is 100 to 1,000 times higher than any local universe relationship predicts. This cannot be produced by the standard model of black hole growth. In the conventional picture, supermassive black holes start as stellar mass seeds, the remnants of massive stars that collapse at the end of their lives. These remnants weigh perhaps 100 solar masses. These seeds then grow by accreting surrounding material. But accretion has a speed limit called the Eddington limit, the point at which radiation pressure from the infalling material pushes back against further accretion. At the Eddington rate, a 100 solar mass seed needs well over 600 million years to reach 40 million solar masses. UHZ1's black hole did it in 470 million years, and that is only if it started accreting the instant it formed, which is physically unrealistic. Natarajan's team published their findings in Nature Astronomy in late 2023. The paper did not merely report a large black hole, it reported a black hole that could not have formed through any known growth mechanism in the available time. And if it could not have grown to this size, it had to have started bigger, much bigger, which meant the origin story for supermassive black holes needed to be completely rewritten. The standard origin story goes like this. A massive star, perhaps 20 or 30 times the mass of our star, exhausts its nuclear fuel and collapses. The core implodes into a black hole weighing maybe 100 solar masses. Over hundreds of millions of years, this stellar mass black hole drifts toward the center of its galaxy, merges with other black holes, and accretes gas from its surroundings. Gradually, limited by the Eddington rate, it grows. After billions of years, it becomes the supermassive black hole we observe at the centers of modern galaxies. This process is called light seed accretion, and it has been the default explanation for decades. UHZ1 broke it. 40 million solar masses in 470 million years from 100 solar mass seed is mathematically impossible at the Eddington rate. Even allowing for brief episodes of super Eddington accretion, where the black hole temporarily exceeds its theoretical feeding limit, the numbers do not work. You cannot grow that much mass that quickly from a small starting point. Natarajan's team proposed an alternative. In the very earliest universe, before any stars had formed, vast clouds of primordial gas existed that contained no metals whatsoever. Metals are critical in star formation because they allow gas to cool efficiently. Without metals, cooling is inefficient, and the gas cloud does not fragment into smaller pieces the way metal-enriched gas does. Instead, the entire cloud can collapse coherently under its own gravity. If the cloud is massive enough and no fragmentation occurs, the result is not a star, it is a black hole. This is the direct collapse black hole model, sometimes called the heavy seed scenario. Instead of starting at 100 solar masses and growing slowly, these black holes start at 10,000 to 100,000 solar masses. A heavy seed of 100,000 solar masses, accreting at the Eddington rate from the moment of its formation, can reach 40 million solar masses in the time available before UHZ1's epoch. The math works, but the heavy seed model carries an implication that rearranges the conventional relationship between black holes and galaxies. In the standard picture, galaxies form first, and black holes grow inside them. In the direct collapse scenario, the black hole forms first. The galaxy assembles afterward from the leftover gas and material orbiting the seed. The black hole is not a passenger in its galaxy, it is the foundation. This would explain the anomalous mass ratio in UHZ1. If the black hole formed before the galaxy, and the galaxy is still assembling around it, then, at early times, the black hole would dominate the total mass. Over billions of years, as more gas falls in and more stars form, the galaxy would gradually outgrow the black hole. The ratio would fall to the 0.1% we observe locally. The ratio is not anomalous. It is a snapshot of a galaxy still under construction. Natarajan has been developing the heavy seed theory for over 15 years, long before JWST launched. The telescope did not inspire the theory. It provided the first observational evidence consistent with it. UHZ1 is exactly the kind of object the direct collapse model predicts. An overly massive black hole sitting inside an undersized galaxy at high redshift. If black holes came before their galaxies, the architecture of the early universe looked nothing like what the standard model assumed, and JWST found an entire population of objects that might be the cocoons where this process played out, objects that match nothing in any catalogue, textbook, or simulation. Starting in 2022, astronomers processing JWST survey images began flagging small red sources that did not fit any known classification. They were compact, unresolved, or barely resolved even in JWST's sharp infrared images. They were red. Their spectral energy peaked at longer wavelengths, and they were numerous, scattered across every deep field the telescope observed. The initial assumption was straightforward. Small red dots in deep infrared images are usually distant galaxies reddened by dust or by the cosmological stretching of light known as redshift. Astronomers tagged them for follow-up and moved on to higher priority targets. By 2024, follow-up spectroscopy had begun, and the little red dots, as the community informally named them, turned out to be something unexpected. Their spectra showed features consistent with active galactic nuclei. Each one appeared to harbor an actively feeding supermassive black hole, but their sizes were wrong. Each one measured less than 1,000 light-years across. for a galaxy hosting an active supermassive black hole that is absurdly compact. Most AGN-host galaxies in the local universe span tens of thousands of light-years. By 2025, 341 little red dots had been catalogued across multiple surveys. They concentrate between redshifts 5 and 10, corresponding to a window from about 500 million to 1 billion years after the Big Bang. Their AGN number densities, meaning the number of active black holes per unit volume of space, exceed predictions from every existing model by a factor of 50. 50 times more active black holes than any simulation produced, and then they vanish. Below redshift 5, the little red dots disappear. No counterpart exists in the local universe. No known type of galaxy, AGN, or compact object in the nearby cosmos matches their properties. An entire population of objects appeared, persisted for roughly 2 billion years of cosmic time, and then ceased to exist without leaving any identifiable descendants. 341 objects matching nothing. That fact alone would make the little red dots one of the most significant discoveries in extragalactic astronomy. But the Rubies survey, analyzing these objects in detail through 2024, found something inside one of them that elevated the mystery from strange to inexplicable. The Rubies team identified a particular little red dot at redshift 3.55 and examined its spectrum carefully. What they found was a Balmer break, a sharp drop in brightness at a specific wavelength caused by hydrogen atoms absorbing photons of particular energies. Balmer breaks are among the most well-understood features in all of spectroscopy. They are diagnostic tools. They tell astronomers the age, temperature, and composition of a stellar population. Astrophysicists have been using Balmer breaks to characterize galaxies for decades. This Balmer break matched nothing. Not a galaxy template, not a standard AGN spectrum, not a quasar, not any combination of known sources. The spectral signature dropped off what the team described as a cliff into territory where no existing model could reproduce the shape. They named it accordingly. The cliff at redshift 3.55 is a spectral feature that belongs to an object for which no theory exists. It sits inside a class of objects that has no counterpart in the modern universe. And a researcher at Penn State was about to bet his career on an explanation that had never appeared in any textbook. Joel Leger is an astrophysicist at Penn State who had been studying the spectral properties of galaxies across cosmic time. In September 2024, he proposed an explanation for the little red dots that broke with every existing classification scheme. The little red dots, Leger argued, are not galaxies at all. They are something that has never been observed before. He called them black hole stars. The concept works like this. In the early universe, a massive cloud of pristine gas collapses directly into a black hole following the heavy seed mechanism that Natarajan described for UHZ1. But instead of the surrounding gas immediately accreting or dispersing, a substantial envelope of gas remains around the newborn black hole. The black hole heats this envelope from within through radiation from its accretion disk. The heated gas glows. It emits light across a broad range of wavelengths. From a distance, the object looks like a galaxy. It has the luminosity of billions of stars. It is compact. It is red, but it is not a collection of stars. It is a single black hole wrapped in a cocoon of hot gas. A black hole star would explain several properties of the little red dots simultaneously. Their extreme compactness becomes natural. There is no galaxy to be extended. There is only a gas cocoon, which can be as small as a few hundred light years across. The strange spectra, including the cliff, become interpretable as the emission of a heated gas envelope rather than a stellar population. No template for a stellar population can match the spectrum because there is no stellar population. The Balmer break is being produced by hydrogen in the cocoon, not in the photospheres of billions of individual stars. The vanishing act also finds an explanation. Gas cocoons are temporary structures. Over time, the black hole either accretes the remaining gas or radiation pressure blows it away. Once the cocoon dissipates, What remains is a naked supermassive black hole. Without the glowing envelope, the object becomes invisible at optical and near-infrared wavelengths. It is still there. It simply stopped emitting in ways that JWST can detect. The little red dots did not die. They shed their cocoons and went dark. If Leha is right, 341 objects in JWST data represent a phase of black hole evolution that nobody had ever theorized before the data forced its invention. An entire category of astrophysical object, visible only during a brief window of cosmic time, that had been completely absent from every model and textbook. The implications extend beyond classification. If these are black hole cocoons, then supermassive black holes in the early universe were even more common than the already elevated AGN densities suggest. Every little red dot is a direct collapse black hole in its chrysalis stage. Leja's hypothesis remains unconfirmed. Spectroscopic tests are ongoing. The theory makes specific predictions about emission line ratios and spectral shapes that can be checked against the data. Confirmation would require ruling out every alternative explanation for the little red dots, and several alternatives still compete for attention. But the black hole star idea was not the most radical proposal on the table. Another team had been working on a theory that went even further, suggesting that some of JWST's most distant objects are individual stars of almost inconceivable mass, kept alive by a fuel source that physics has never directly observed. Dark matter. The idea came from Catherine Fries at the University of Texas at Austin. In 2007, years before JWST launched, Fries and her collaborators published a theoretical framework for what they called dark stars. The name is misleading. They are not dark. They are among the brightest objects the theory predicts. The dark refers to their fuel source. In standard stellar physics, stars burn through nuclear fusion. Hydrogen atoms slam together at millions of degrees, fuse into helium, and release energy. Dark stars would not. They would be powered by the annihilation of dark matter particles inside a primordial gas cloud. Dark matter makes up roughly 27% of the universe's total energy content. It has never been directly detected. No instrument has ever captured a dark matter particle, but its gravitational effects are measurable everywhere. Galaxies rotate too fast for the visible matter they contain. Galaxy clusters hold together with far more force than their luminous mass can explain. Something invisible is doing the work. Fries's proposal was specific. In the earliest epoch of the universe, before any normal stars had formed, dense halos of dark matter would have collected around clumps of primordial gas. If dark matter consists of particles that can annihilate when they collide with each other, which several leading candidates predict, then those annihilations would release energy into the gas cloud, enough to heat it, enough to prevent it from collapsing into a normal star. Instead of a compact, hot object burning fusion fuel, you would get something enormous, a single star with a mass up to 1 million times that of our star, as luminous as an entire galaxy. And here is where JWST enters the picture. When astronomers point the telescope at the most distant objects in the universe, they see bright, compact sources at extreme redshifts. They assume those sources are galaxies containing millions or billions of stars. But a dark star of 1 million solar masses would look almost identical in JWST imaging data. Same brightness, same compactness, same redshift. You cannot tell them apart with images alone. In 2023, Fries's team flagged 3 photometric candidates in JWST data consistent with the dark star model. The objects had been classified as early galaxies. Their brightness and color profiles matched what dark star theory predicted, but photometry only tells you how bright something is and what color it appears. It cannot tell you what the object actually is. For that, you need spectroscopy. You need to split the light into its component wavelengths and read the chemical fingerprint. Photometry is a photograph. Spectroscopy is a blood test. And in 2023, nobody had the spectroscopic data to confirm or rule out dark stars in those candidates. They could be galaxies. They could be something that had never been observed before. The distinction mattered enormously. If even a fraction of JWST's most distant galaxies turned out to be individual dark stars, the census of the early universe would need rewriting from the ground up. The number of galaxies at high redshift would drop, the inferred star formation rates would change. The impossible masses that launched the entire crisis might partially dissolve because some of those bright dots were never collections of stars at all. They were single objects, burning a fuel that physics has spent decades trying to detect. Spectroscopy was the only path forward, and in October 2025, a spectral line appeared that nobody had expected to find. The target was JWST GSZ 140, the most distant spectroscopically confirmed galaxy in existence, sitting at redshift 14.32. Light that left this object when the universe was just 290 million years old. The Stefano Carniani's team had already confirmed its redshift using roughly 10 hours of near-infrared spectrograph observations. They had detected oxygen in its spectrum, which was strange enough, but a separate analysis of that same spectral data, published in October 2025, found something else buried in the signal: a tentative absorption feature at 1,640 angstroms, helium-2 absorption. To understand why this matters, you need to know what helium-2 is. Regular helium has 2 electrons. Ionize it once, strip away 1 electron, and you get helium-1. Ionize it again, strip away the second, and you get helium-2. Fully ionized helium. The energy required is extreme. You need photons with wavelengths shorter than 228 angstroms, which means temperatures far beyond what normal stellar populations produce at this epoch. In the modern universe, you find helium-2 emission near the most violent objects, quasars, Wolf-Rayet stars, active galactic nuclei. But at redshift 14, 290 million years after the Big Bang, none of those sources should exist yet. Normal stars at this epoch would have been predominantly hydrogen-burning, incapable of producing the hard ultraviolet radiation needed to doubly ionize helium. And yet, there it was. A dip in the spectrum at exactly 1,640 angstroms. The dark star model predicts exactly this signature. The extreme temperatures generated by dark matter annihilation inside a supermassive dark star would naturally produce hard ultraviolet radiation capable of ionizing helium twice over. A dark star of several 100,000 solar masses would show helium-2 absorption at precisely this wavelength. The signal is tentative. The signal-to-noise ratio hovers around 2, which in astronomy means you can see it, but you cannot bet your career on it. A signal-to-noise of 5 is the traditional threshold for a confirmed detection. It could be real. It could be an artifact of the data reduction pipeline. It could be noise that happens to land at an interesting wavelength. But if it is real, the consequences restructure multiple fields simultaneously. It would mean the most distant confirmed object in the universe is not a galaxy. It is a single star, powered by a substance that has never been directly detected. The first observational evidence that dark matter interacts with visible matter in a way that produces light. 27% of the universe caught influencing the objects we can see for the first time. It would also mean that an unknown number of other bright, compact, high redshift objects in JWST data might be dark stars misidentified as galaxies. The early universe's population census could be fundamentally wrong. We assumed we knew what we were looking at. Confirmation requires deeper spectroscopy, more integration time on the same object, or observations of the other dark star candidates. JWST has the capability. The question is whether it gets the telescope time, which is allocated competitively and in high demand. The tentative detection sits in the literature, a whisper at 1,640 angstroms. And while astronomers debated whether JWST 140 might be a dark star, another spectroscopic analysis of a different object was revealing a chemistry problem that had no solution at all. GNZ11 sits at redshift 10.6, 430 million years after the Big Bang. For years before JWST, it held the record as the most distant galaxy ever observed, detected first by the Hubble Space Telescope in 2016. JWST turned its instruments on GNZ11 in 2023, and Roberto Maiolino's team at Cambridge used the near-infrared spectrograph to pull apart its light with unprecedented precision. What they found was nitrogen. Specifically, the ratio of nitrogen to oxygen in GNZ11 was 4 times higher than the ratio measured in our star. This is a problem that sounds technical, but carries a straightforward consequence. Nitrogen, in the amounts detected, cannot be produced quickly. Under standard chemical evolution models, you need intermediate mass stars, objects between roughly 2 and 8 solar masses, to cycle through their entire lifetimes. These stars burn hydrogen, then helium, then produce nitrogen through the carbon-nitrogen-oxygen cycle in their cores. When they die, they expel that nitrogen into the surrounding gas through planetary nebulae and stellar winds. The next generation of stars incorporates it. The nitrogen-to-oxygen ratio builds up gradually, generation by generation, over timescales measured in hundreds of millions to billions of years. 430 million years is not enough. The universe at that age had not existed long enough for multiple generations of intermediate mass stars to live, die, enrich the gas, and build up nitrogen to 4 times the solar ratio. The math does not close. Maiolino's team proposed an alternative source: supermassive stars. Not the dark stars, powered by dark matter that Fries described, but a different class of theoretical object. Stars between 1,000 and 100,000 solar masses, formed through runaway collisions in extremely dense stellar clusters. In environments where young stars are packed close enough together, gravitational interactions can cause them to merge repeatedly. Objects of extraordinary mass build up in just a few million years. These supermassive stars would burn hot and fast. Their interiors would reach temperatures where the carbon-nitrogen-oxygen cycle runs at maximum efficiency and shedding nitrogen-rich winds continuously throughout their short lives. A supermassive star of 10,000 solar masses could enrich its surrounding gas with nitrogen in roughly 1 million years. That is fast enough to explain GNZ11, but it requires conditions that no simulation has fully reproduced. The stellar densities needed for runaway collisions are extreme. The clusters would need to be far denser than anything observed in the modern universe. Stars packed so close together that collisions become inevitable rather than rare, and supermassive stars of this type have never been directly detected. They remain theoretical objects, invoked because the data demands them, not because anyone has seen one. Necessary, perhaps, but unproven. The nitrogen problem in GNZ11 was not alone. JWST already had oxygen at 290 million years. Now, GNZ11 had nitrogen at 430 million years. 2 different elements, 2 different objects, 2 different epochs, both demanding chemical enrichment that outpaces every standard model. Each finding could be treated as an isolated anomaly, a single unusual object with unusual chemistry. But isolated anomalies have a way of accumulating, and the next chemical detection would turn 2 anomalies into a pattern that could not be dismissed. Polycyclic aromatic hydrocarbons are large molecules built from interlocking rings of carbon and hydrogen atoms. The name is technical, but the substance is common. On Earth, you encounter them in barbecue, smoke, diesel exhaust, and charred meat. In space, they are everywhere. They fill the gaps between stars. They coat the surfaces of meteorites. They are so abundant in the Milky Way that their spectral signatures show up in nearly every observation of the interstellar medium. Astronomers know how polycyclic aromatic hydrocarbons form. Carbon-rich stars, in the asymptotic giant branch phase of their evolution, shed their outer layers in slow, dense winds. As that material cools and expands, carbon atoms bond into increasingly complex structures. Rings form, Rings connect to other rings. Over time, the interstellar medium becomes enriched with these molecules. The process requires evolved stars, which means it requires time. Asymptotic giant branch stars are not young. They are intermediate mass stars in the final stages of their lives, after they have burned through hydrogen and helium and begun expelling their outer envelopes. To reach this stage, a star of a few solar masses needs somewhere between 100 million and several billion years. Then the molecules themselves need time to accumulate in sufficient quantities to show up in spectroscopic observations. The conventional estimate for a galaxy to develop a detectable polycyclic aromatic hydrocarbon signature was roughly 1 billion years of stellar evolution. Enough generations of asymptotic giant branch stars living, dying, and seeding the gas with carbon molecules. JWST detected polycyclic aromatic hydrocarbons at redshift 6.7. The universe at that redshift was approximately 900 million years old. That is barely within the theoretical minimum, and only if you assume the most generous possible conditions. Stars forming immediately after the Big Bang, the fastest possible evolution to the asymptotic giant branch phase, maximum carbon yield per star, efficient mixing of enriched material into the surrounding gas, every parameter pushed to its optimum, and even then, the numbers are tight. 900 million years is not a comfortable margin, it is a razor's edge. Now lay the three chemical detections side by side. Oxygen at 290 million years in JADESGSZ140, nitrogen at 430 million years in GNZ11, polycyclic aromatic hydrocarbons at 900 million years at redshift 6.7, three independent chemical signatures, detected in three different objects, at three different epochs, by three different analysis teams. Each one individually pushed the limits of what standard stellar evolution allows. Together, they say something that none of them says alone. The early universe's chemistry was mature almost from the start. It did not build up slowly over billions of years, the way textbooks describe. Complex elements and complex molecules appeared in the first few 100 million years, as though the chemical clock started running before the universe gave it permission. This was no longer a galaxy formation problem. It was no longer a black hole growth problem. The chemistry of the early cosmos was wrong too. Every timeline that cosmology relied on, for stars, for galaxies, for black holes, for dust, for molecules, was landing shorter than the observations demanded. And, if the timeline was wrong for the objects inside the universe, that raised an obvious question about the biggest timeline measurement in all of cosmology, the one that tells us how fast the universe itself is expanding, because that number was in trouble too. There is a number in cosmology that measures how fast the universe is expanding. It is called the Hubble constant, named after Edwin Hubble, who first demonstrated in 1929 that distant galaxies are moving away from us, and that the farther away they are, the faster they recede. The Hubble constant expresses this rate. Its units are kilometers per second per megaparsec. For every megaparsec of distance, roughly 3.26 million light-years, a galaxy moves a certain number of kilometers per second faster. Measuring this number should be straightforward. It is not. For decades, the problem was that nobody could measure it precisely enough. Different methods gave wildly different answers. Estimates fell anywhere from 50 to 100. By the 2000s, precision improved dramatically. Two approaches emerged as the gold standard. The first is the local distance ladder. Adam Riess, who shared the Nobel Prize in 2011 for discovering the accelerating expansion of the universe, leads the supernova H0 for the equation of state team. His method uses Cepheid variable stars as distance markers. Cepheids are stars that pulse with a period directly related to their intrinsic brightness. Measure the pulse period, calculate the true brightness, compare it to the observed brightness, and you get the distance. Calibrate enough Cepheids, then use them to calibrate Type 1a supernovae at greater distances, and you can build a ladder that reaches across the observable universe. Rias's team gets 73.0 kilometers per second per megaparsec. The second method skips the local universe entirely. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped the cosmic microwave background. This is the afterglow of the Big Bang itself. Radiation released when the universe was just 380,000 years old. By analyzing the precise pattern of temperature fluctuations in that radiation, physicists can extract a prediction for what the Hubble constant should be today, assuming the standard cosmological model is correct. Planck gets 67.4, 73 versus 67.4, an 8% gap. For years, the assumption was that one of these measurements had to contain a systematic error. Maybe the Cepheid distances were wrong. Maybe dust was reddening the light. Maybe stellar crowding in other galaxies was throwing off the brightness measurements.